so far all we've been concerned with is things moving in a straight line. But obviously not everything moves in a straight line. So if we're not moving in a straight line, then theoretically the only other thing we're doing is moving in a circle or an arc of a circle. It might be a really tiny arc because we might only go, ooh, just turn a little bit. But it's either got to be linear or circular. So let's have a look at this idea of circular motion then. We have a thing called angular velocity. So here's our circle. O is obviously the centre, R the radius. And all the angular velocity is, well, if I move from A to P, I'm going to sweep out some angle, theta. We could call that the angular displacement. That's how much of an angle we've displaced. Well, the angular velocity then would be the rate of change of that angle. So d theta to t, although we commonly use omega as the symbol for angular velocity. But again, it could also be thought of as d theta to t, or theta with a dot, those we could have as well. And it's measured in, well, how many radians we sweep out, usually per second. Well, linear velocity, how do we compare the two? We have our circular motion, we have our straight line motion. That's fine to know how fast the angle is changing, but we're more interested in how fast the actual particle is going itself. So at any instant, if we want to know how fast it's travelling, the way I tend to think of it is it's like if at that instant I cut the string that's joining the point to the centre. And if I was to cut the string, I would shoot off at a tangent. And so that's why it's also sometimes known as tangential velocity. There it is. Woo, off it goes. Okay. So how to work it out? If I let the length of that arc be x, we remember that x is equal to the radius times theta. So x, which would be the linear displacement, how far we've moved along the curve, if I was to differentiate that with respect to time, that would be equal to, well, r is just a constant, times d theta to t. Well, dx to t is our linear velocity, and d theta to t is our angular velocity. And so that's how we relate the two together. It is simply velocity equals r times angular velocity. So really, it's the same as the formula we saw for finding the length of an arc, because it was length is equal to the radius times theta, but now we're just taking it to the next level. We're just differentiating both. So velocity is equal to the radius times the angular velocity. So period. Time it takes for one revolution will be 2 pi divided by the angular velocity. So 2 pi divided by omega. So again, very similar to where we saw our period in trig, where it was 2 pi over n. So similar sort of formula. All right, let's do a quick example here. Satellite, it's moving in a circular orbit. It travels around the planet Earth, by the way, of 20 revolutions per day. How fast is that in radians per second? Okay, well, one revolution would be 2 pi radians, so 20 times 2 pi gives me 40 pi radians per day, but we want per second, so divided by 24 times 60, and we get pi on 2,160 radians per second. So it doesn't seem to be moving that quick, because if you think about a radian, well, pi, 3.141592, etc., 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 but divided by 2,160, so every second sweeping at a very small angle. But how fast is it actually going? Because when we take into account the radius of the satellite's actually quite a long way up. About 9,000 kilometres from the centre of the Earth is the orbit of satellites. Well, all right, let's work it out. R times omega, but that would be in kilometres per second. Now it's getting quite large when you think about it. 9,000 times pi, times 3.14, divide that by 2,160 kilometres per second, turns out to be moving quite quick indeed. 15,000 pi kilometres per hour. So I guess all we can conclude from this is lucky there's no police up in space, because as it would be traveling over a school zone, big trouble, okay? All right, so 9A, that's all I really want to do today. It's just that introduction to the idea of circular motion.